Hi. In the last class, we discussed geographical distances, how to measure geographical distances by applying rules of trigonometry. In this class, we discuss how to determine much larger distances, cosmological distances, distance to star, distance to sun, distance to satellite, etc., where we apply some aspects related to circle. So before entering into the subject, we first discuss some aspects of circle. Okay. Look here. See, in a circle, the total angle around the central point is 360 degree. Sometimes we express the angle, total angle, in terms of radian also. So first we will see what is radian. Imagine in a circle, an arc whose length corresponds to the radius of the circle itself. Look, for example, in this diagram, this is the radius or this is the radius, and this arc is having the same length as this or this radian. Then the angle covered by that arc at the center is called 1 radian. We know the total angle in degrees is 360 degree around a point. Okay. And here the angle 1 radian is 57.3 radian. 57.3 degree. 1 radian is equal to 57.3 degree. And in that case, the total angle is obtained by, in terms of radian, is obtained as 2 pi radians. The whole circle has the angle 2 pi radian. So we have to remember that 360 degree and 2 pi radian are equivalent. 2 pi radian does not mean 2 pi r. 2 pi radian. Radian is a measure of angle. Okay. So we have to remember that 2 pi radian and 360 degree are equivalent terms regarding the total angle in a circle. Okay. Now, in the next, look here. 360 degree is 2 pi. Therefore, 1 degree. 2 pi is 3.14. So 2 into 3.14 by 360. You know how we get the value of pi. Pi is nothing but the ratio of circumference, total circumference divided by diameter. That ratio is always a constant for all circle, which is 22 by 7. For any circle, ratio of the circumference to 2r or diameter is a constant, and that constant is commonly known as pi. So its value is 3.14. So 1 degree is equal to 2 into 3.14 by 360. 360 degree is 2 pi. Therefore 1 degree 2 pi by 360. That is 1.74 into 10 to the power of minus 2. So please remember, 1 degree in terms of radian is 1.74 into 10 to the power minus 2. And we know 1 degree is further divided into 60 minutes. So 1 minute is 1 by 60 degree. You see, in terms of radian, it will be this divided by 60, which is this value. So 1 degree is this much radian. Okay. 360 degrees 2 pi radian. 1 degree is this much radian. 1 minute, this divided by another 60, this much radian. Okay. And 1 second, like time, angle is also divided into minute and second. So a second will be this divided by 60 or this divided by 3600. Both are same. So we get 4.84 into 10 to the power of minus 6 radian. If it's possible, you can make all these things by heart. 10 to the power of minus 2, 10 to the power of minus 4, 10 to the power of minus 6 are the powers. but the values are not in a particular sequence, 1.74, 2.91, 4.84. If you make them by heart, it would be much easy for, much time saving in entrance examination, etc. Again, one more thing we can make by heart if possible. 1 radian is equal to, this is 2 into 3.4. Therefore, 1 radian will be, you take 2 pi to the other side. 360 by 2 pi, 360 by 2 into 3.14, 57.32 degree angle. So, if you make all these things by heart, it will be much helpful for you to save time in the entrance examination hall. Okay. Now we will see how we are going to use this information regarding a circle in measuring large distances. For that, we have to know what is parallax. See, this is the simplest example everybody used to say. If you keep your finger like this in front of you and watch this finger with one eye closed and one eye open, first using left eye and then using right eye or vice versa, you will see an apparent shift in the position of your finger, isn't it? With respect to the background. With respect to the background, since there is only background, you realize that there is a shift. Otherwise, you will never know. Okay. With reference to the background, you feel there is a shift in the position of this finger. This apparent displacement of a body, of any object, due to different point of perception, is called parallax. Okay. So, it is here we measure large distances by making use of this phenomena called parallax or parallactic shift. Okay. How we are going to apply that, we will try to understand. Look here. See, suppose this is a far distant star. This is a far distant star. And you are observing that star. Suppose you are observing that star from the two poles of the earth. Two diametrically opposite poles of the earth. Let this circle be our earth. Listen, let this circle be our earth and let it be its diameter. Okay, this circle is our earth and that D is its diameter. Okay, see, since we are measuring very large distance, we cannot choose depend upon our eye alone, because the distance between these two eyes are extremely small compared to cosmic distances. So here we want two different point of observation. Unlike two eyes, we want two distinct points of observation. So in this experiment, one eye is here and the other eye is on the diametrically opposite point on the diameter. Now you look at the star here. In the first case, the vision axis is like this, and in the second case, the vision axis is like this, and there is an angle, okay, in between these two. Okay, that is the, here we express the parallactic shift in terms of angle, but we may use the normal degree angle or minute angle or second angle, or here we are adopting the radian angle. This theta is expressed in radian. Okay. Now, listen carefully. Listen carefully. Imagine a huge circle whose origin or center is this star. Okay. And its radius is this much, the distance we want to know. This is the distance between our viewpoint and the star. This is the radius we want to measure. Imagine that circle. Imagine that huge circle. Okay, let it be there. Now listen. Circumference of a circle divided by total angle in radian. What is the circumference of a circle? It is 2 pi r. Okay. What is the total angle in radian? 2 pi. So, total circumference divided by total angle ratio is 2 pi r by 2 pi, isn't it? Now imagine about the theta radian angle. How much circumference it covers? This A. A is this arc length. This arc length is covered by this theta. When the total length is 2 pi r, total angle is 2 pi. When the total length is only A, what is the angle theta? So 2 pi r by 2 pi and A by theta must be the same because they are in proportion. When A increases and become the total circumference 2 pi r, theta increases and become the total radian angle 2 pi. You got the logic? So since the numerator is proportional to numerator, denominator is proportional to denominator, these two ratios are the same. 2 pi r by 2 pi is equal to A by theta. Hope you understood that. We are referring to a huge cosmic circle. Imagine the cosmic circle. Then here 2 pi and 2 pi cancels. What remains? R. R is equal to A by theta. R is equal to A by theta, or theta is equal to A by R. A is the arc length. A is the arc length and R is the radius of that huge circle. Now we change the symbols to get a general form. See here, this arc length is approximated to be the diameter. Why approximate? Because arc length is not a line, straight line. It is partly a curve. But when you compare such a huge planet, this value can be approximated to be this, especially when theta is very small. See the angle, the parallactic angle is when very small. There is nothing wrong if we approximate this diameter with this arc length. That's why in book we say that d by d is equal to theta when theta is very small. When theta is very small, the curve can be approximated to be the corresponding straight line. So what we do, we replace the arc length A with the diameter symbol D. Arc length is replaced by diameter D and radius R of the cosmic circle is replaced by the distance which we want to calculate, the distance to the star, etc. So now we have this equation, theta in radian is equal to d by d. So this is the most common equation we use in evaluating distances to stars, other planets, etc., etc. Okay. What is written below? In cosmological measurements, theta is parallactic angle in radians. We have already mentioned that. Comma r is equal to d, the distance to the cosmic body like star, etc. And a approximately equal to d, the distance between the two observation points. That is A, the arc length, is the distance between the two observation points. In many cases, it is the diameter of Earth, but that is not a must. You may choose two other positions on the Earth's surface. The only thing is that you must know the direct distance between them. That's all. Okay. So now we know which equation to be used to determine the distances. Okay, to far distant stars, etc. Even then, there is a restriction. See, when this angle is extremely small, there can be error in the calculation also. That we have to remember. Okay. Now some basic lengths we have to make by heart. Okay. One is one astronomical unit. You know, one astronomical unit is the average distance between Sun and Earth. Okay. One astronomical unit is the average distance between. We know that distance vary. So we take the average. it has been found to be nearly 1.50 into 10 to the power 11 meters. We are studying all in meter. In many time in questions it may have appear in kilometer, so you have to take care regarding that. 1.50 into 10 to the power 11 meter. Then light year. We know light year is the distance traveled by light per year. Okay, its value is much greater than this, 9.46 into 10 to the power 15 meter. Okay, that is one light year. And thirdly, parsec, one parallelistic second or one parsec. Its definition is like this. It is the distance that tends an angle of 1 second, tends an angle of 1 second. It is that much a distance, 1 parsec is that much a distance which one astronomic unit can tend at a point. So that much distance which brings an angle of 1 second for one astronomic unit length is 1 parsec. So they are related like that. So you can even calculate a parsec. How? We know theta is equal to d by d. We determine that. How we can calculate parsec from astronomic unit and this angle. Look here, we know theta is equal to d by d. For us, theta is 1 second. We convert that 1 second to degree. How? 1 second by 3600 gives you degree. Okay, in value in degree. And we know every 360 degree is 2 pi radian. In that case, this much degree is how much radian. So we have converted 1 second to what? Radian value. Or you can by heart the other value and directly substitute. That's the easy way. This is equal to, what is d here? The two observation point length AU, 1 AU by d. This d will be, if you take this as 1 and if you use this small d as AU, the d, capital D, now you calculate will be 1 parsec. So parsec is a special kind of definition. Okay. Okay. This is the first problem. A distant star has a parallax angle of 0.723 arc second when measured from the same location within 6 months gap. What is the distance of the star? You know what is the specialty of 6 months? Within 6 months, Earth rotates, completes half its revolution around the sun. Okay. Then, this distance, that is the distance between the two positions, which is our small d, corresponds to twice the astronomical unit. Means distance between sun and earth is 1 astronomical unit. So within 6 months this distance will be doubled like this. So this small d is 2 astronomical unit. The angle has been given to be 0.723 arc second, which we call second. And we have to find this distance between earth and that star. Here we assume that the star is remaining in its original position. Okay. How we do that? See, first we may convert the arc second to radian. How? 0.723 divided by 60 and another 60 to convert it into degree. And we know 360 degrees 2 pi. So this much degree is how much? That is equal to, so this much radian is equal to small d, which is 2 into AU by capital D. Rearrange, capital D is equal to, you have to do this much operation, you get a 8.56 into 10 to the 16 meter. Okay, it involves a bit of calculation. But if you make the other thing by heart, we have studied that 1 arc second is equal to 4.84 into 10 to the power of minus 6 radian. If you have that value by heart, much calculation will be reduced. And so D is equal to, now you can use this term directly. So D is equal to 2 AU by arc second converted to radian. So 0.723 into 4. The conversion factor 4.84 into 10 to the power of minus 6. So this is the radian. Okay, this is the radian angle. Then you easily get the same answer, 8.56 into 10 to the power of minus 16 meter. Okay. One thing, see, by repeated solution, while you use these conversion factors repeatedly, by attempting more and more problem, these values become automatically by heart. You don't have to put special effort to make them by heart. If you are supposed to do much and much problem to speed up. In that way, you can make these conversions factors by heart. So you are supposed to do so many problems. Okay. Now look at the next problem. The parallactic angle when the same planet is observed from two diametrically opposite points on Earth's surface at the same time was 1 minute. The angle was 1 minute. The distance of the planet is. Here what is the main difference from the previous problem? In the previous problem, we were observing from the same point and the time changes. Time lags by 6 months. Here we are measuring at the same time from two different points. Okay. So there's a distance between the observation points here. So look, it appears like this. One person is observing from here. The other person is observing from here. This is 2r. Here small d is equal to 2r. We want to find this. The angle has been given to be 1 minute. Here the planet is keep on moving now. So we have to make the measurements at the same time, unlike the case of star. The star is almost practically static. That's why we could make the measurement there. Practically static. Okay. Here the planet is not that distant and it is keep on moving. So we cannot wait for 6 months. So we have to make the measurement at the same time. Okay. Hope you understood that. Okay. Now, theta, 1 minute, 1 by 60 degree into 2 pi, conversion factor to radian 2 pi by 360 is equal to d by d. 2 is twice the radius. The radius has been given in the question. Earth's radius has been given. So 2 into r, rearrange, you get a d. That involves more calculation. If on the other hand, you can do it by shortcut by remembering that 1 minute is 2.9 into 10 to the power of minus 4 radian. Then you can use that value. 1 minute is 2.9 into, you can easily cross multiply because you now substitute this in radian. So d is equal to d by that angle in radian. D by 2.9 into 10 to the power minus 4. Numerator 2 into capital R. Radius of the earth. 2 into 64, 5 zeros divided by 2.9 and same value you get. Okay. Next is a assertion reason type question. It has come for IIT JEE area. Assertion. Parallax method is used for measuring distances of nearby stars only. Reason. With the increase of distance from the star, the parallactic angle becomes too small to be measured accurately. This type of assertion reason type question, we know how the ABCD comes. Both statements are true and the second statement justifies the first statement. Both statements are true. Second does not justify the first statement. Only first statement is correct. Only second statement is correct, like that. Here, see, both statements are correct. Far distant stars distance cannot be measured by this method, because in that case the angle becomes so small that its exact measurement become very difficult. If at all we make a measurement, that involves much percentage error. So here both statements are correct, and the second statement, which is called reason justify the assertion. Okay. Next problem. Diameter of Earth is given. A distant star produced a parallactic angle when observed at the same time from the two ends of an imaginary chord of Earth, whose length is radius of Earth. The distance of the star in light years. Simple. See, here the difference is, here the thing is that here two persons are observing from the two ends of an imaginary chord of Earth, which is equivalent to its radius. So this is R. Okay. Angle is 1 second. The distance. So simple. So here I am directly using the conversion factor. 1 second is 4.84 into 10 to the minus 6 radian. Then that much value is distance d is R here by capital D. So capital D is equal to cross multiply. You get 1.3 into 10 to the 12 meter. To convert that to light year, you divide it with the light year's meter equivalent, which is 9.46 into 10 to the 15 meter. If you divide, you get 1.37 into 10 to the minus 4 light year. A fraction light year only. Okay. Okay. The last problem. A huge meteor is orbiting around Earth at a height of 24,000 kilometers. Earth is static with respect to the meteor because Earth is moving along with the meteor. So it is static with respect to the meteor. What is the speed of the meteor if after 5 minutes the meteor becomes visible at an angle of 20,500 second, 20,500 second with respect to initial position, 20,500 second with respect to initial position. Within this reach, the journey is almost linear. Within that 5 minutes, imagine the journey of the meteor is linear. Then you get the answer. Okay. Here, look what is the picture here. This is Earth's surface. We are observing a meteor and that meteor covers this much angle, 20,500 second within 5 minutes, and this distance has been given. So we want to get this distance. Okay. So capital D is known, small d we have to calculate. See the system, the whole system is moving. At the same time, this meteor is rotating also. So the Earth's speed and corresponding speed, that cancels out. So it is as if the Earth is static and this alone is rotating. You have to remember that. Okay. Now, look here. First we convert this second to radian. 20,500 seconds is equal to 20,500 into 4.84 into 10 to the minus 6 radian. Now use the equation theta is equal to d by d, or small d is equal to theta into capital D. 20,500 into 4.84 into 10 to the minus 6 into distance 24,000 kilometer. You get 2381.3 kilometer. Okay. That's the distance covered within 5 minutes. So speed is distance by time. 2381.3 divided by 300 second. You get a 7.94 kilometer per second. I have awarded the options. The option is 7.94 kilometer per second. Hope you understood these things. Okay. Right. See, in the problems we have discussed, we have mentioned about the parallactic angle generated by a distant star to our observation. Okay, this angle. How that can be measured? The thing is that you cannot measure that directly because you don't know this distance, because we are in the pursuit of finding that distance. So how you get that angle? In order to get that angle, while you start experimentation, you have to find another star which is far beyond this star. Okay. And first you observe that star just above. And you are observing through the telescope and make its reading 0 when you see this star. Okay. Now you start turning the telescope until you see this star under concern. Then there will be an angle registered there. Okay. Similarly, you again see the same star will be seen overhead here also, because it is much far beyond. Okay, so the same star will be observed like this when you view from here. Okay, then do the same thing. First you observe this star, make the telescopic reading 0, turn it until you see this star. Okay, then the registered angle is another theta. So let it be theta 1 and theta 2. Now imagine a line drawn just perpendicular to the Earth's surface. If this is theta 1, this angle also will be theta 1. If this is theta 2, this angle also will be theta 2, because these two lines are parallel, or these two lines are parallel. So this angle plus this angle will be this angle. Thus we get the parallelectic angle. Hope you understood that.